my name is Justin Mao. I did my project on quantum key distribution, or QKD. So a little background, as we know, a lot of these cryptography standards that we use today are built around infeasibility. So computers nowadays can't really break a lot of these cryptography standards because either they're computationally complex and generally very time consuming to use a normal computer for. For example, there's RSA, where you can know the product of P and Q, two prime numbers, but from those you can't really reverse engineer that, or you can't reverse engineer P and Q, at least for now. And so comes in quantum computing. So basically what quantum computing is rather than bits like on a standard computer, it deals with qubits. And so they have the traditional two states, so like with a normal bit of 0 and 1, but it also has two ground states, the ground 0 and ground 1. And this image kind of shows that a little bit there. Quantum computing also relies on three main basic properties of just quantum mechanics and physics in general. One is superposition, and so with this, the quantum computer can be simultaneously in multiple states rather than just in discrete states, one at a time. Another is entanglement, where qubits and objects are permanently entangled together. So you'd have two qubits, where if you observe one, then the other one gets affected. And so with this, you can examine 2 to the power of n states at once on a quantum computer on an n-qubit machine. And the third one isn't too important for this presentation at least, but it's interference. And so that's basically used to control these different states. And so if there's a signal that's producing a correct answer, that signal gets amplified. If it's producing a wrong one, they try to cancel it out. And a common misconception about a lot of quantum computing is that it's not necessarily faster than traditional computers. A lot of people think it's that because it's quantum, it's way better than anything we have. But the truth is, it's much faster on a certain subset of problems, oftentimes mathematically intense problems, which, in the case of cryptography, include factorizing large integers, which leads to determining P and Q, which kind of renders our current cryptography somewhat obsolete. So what does this mean for encryption? Well, like I said, the calculations required, say, to break P and Q and find those and break the RSA, those kind of calculations are exactly what quantum computing is great at. Whereas current encryptions on our current computers, it may take hundreds of years to crack on current computers. The quantum computers can do it in a much, much shorter amount of time. However, as it is, quantum computing is still not really advanced enough to be a huge threat currently, but as we know, technology moves pretty quickly, and once it becomes commercially available and hackers and malicious parties can kind of get their hands on some of this, it might make our cryptography standards meet. So quantum key distribution is one proposed solution. It's essentially a cryptography protocol based on actual quantum computing itself. And so what this does is there's an encryption key that gets distributed via quantum systems. And so in this case, it would be transmitting photons over fiber optic cables from one quantum computer to another. There are two main categories of these, one of which is prepare and measure, which is kind of what we'll go in more in depth into one of the protocols for that, in which case it measures the unknown quantum states of these photons, and the way it's set up, it can detect eavesdropping. So if someone's peeking in and trying to steal some of this data, they can tell that one. And the other one is entanglement based. So in this case, it's using the entanglement property. I'll talk about that in a bit. Of where you observe one value, it'll change the corresponding entangled qubit. And so that way, if someone intercepts the message, it'll kind of scramble it, and you can, the receivers will be able to tell that someone tried to access this data. So the property of quantum entanglement is that when one observes a particle's property, the entangled particle would instantaneously be observed in the opposite state. So if you have something that's, say, it's either positive or negative, and you have two of these ions or whatever tied to one another, quantumly entangled to one another, if you observe one and look at it and see, okay, this one's positive, then the other one that's entangled to it will automatically become negative. And it doesn't matter the distance between them. One important property of this is that you can't predict the observed state beforehand, so you can't know whether it's going to be positive or negative before you actually check it. And so the way this is set up, for key distribution, you'll still need a classical communication channel to discuss these observations. Another important property for a lot of these is the Heisenberg uncertainty principle. And so that's defined as, in a quantum system, only one property of a pair of conjugate properties can be known with certainty. And for example, the example that Heisenberg uses is with an electron. You cannot measure the position of it without disturbing the momentum, and vice versa. So if you try to actually get the momentum property, then that ruins the position. You can't tell what the position is anymore. Or if you calculate position, that's going to disturb the momentum, and now you won't know what that is. And so in the case of quantum key distribution, you use the conjugate property of the polarization of a photon. And another important theory and theorem that kind of developed from Heisenberg uncertainty principle is that it is the no-cloning theorem, wherein it is impossible to create identical copies of an arbitrary unknown quantum state. So that way you can't just make duplicate copies of these photons in these states, and then if you guess incorrectly or whatever, you can't determine what the actual state was. And so the protocol I'm going to talk about today is the BB84 protocol. It was designed by Charles Bennett and Gilles Broussard in 1984, and this is heavily based on the Heisenberg uncertainty principle. And so what this does is you first encode the secret key in the polarization of photons. And the way it's set up is if an eavesdropper measures these values, it'll be pretty obvious, you can tell. So the first step here is encoding these bits. That's how it happens. You can either encode it as a polarization in a rectilinear base or a diagonal base. And so what that means is in a rectilinear base, like on the left here, it kind of shows it. If you have a binary 0 for that bit value, you can encode that as 0 degrees in the rectilinear bases. If you have a 1, you can encode that as 90. If you choose the diagonal base, however, then a binary 0 would encode as 45 degrees, and a binary 1 would encode as 135 degrees. And so, the first part here, say you have Alice and Bob. Alice will first choose a random string of bits, say 0110101. Put that in the table there. She'll then randomly choose a basis for each one of these bits. So, say for the first bit, she'll choose the rectilinear basis, and then for some of the other ones, she'll just do it at random for each of these. And then from there, it calculates the polarization. So the next step is Alice sends these she sends these photons over to Bob, and he'll receive them via the quantum channel. And there's Alice's bits for reference. And what he does is kind of the same. He'll randomly choose a basis for each one of these photons, like so, and then he'll measure each of the photons' polarization. And as you can kind of see, a lot of these are, some of them he guessed correctly and got the same polarization, but other ones he guessed incorrectly, got some random other one. And so that leads to the next step, where once they have these polarizations on an insecure channel or just a standard communication channel, Bob will tell Alice what basis he used for each of those photons. So he'll send that over to Alice. Alice will check that and then respond and tell him which of them were correct. So in this case, the first, the third, the sixth, and the eighth were all correct. So from there, both of them know which ones are incorrect, and so now they both discard those corresponding bits. So say the second one was incorrect, they get rid of that. The fourth one, the fifth one, the seventh one. And so what they're left with is called the sifted key, which is their shared secret key. And so as long as there's no errors or manipulation along the way. And so the shared secret key in this case would just be 0101. Those are the remaining ones. And now for the last part, because they have the secret key, but they need to make sure that no one was eavesdropping. And so to check that, they first agree on a random subset of the bits to compare. So say they'll choose, the second and last bit. And so they'll send those on an unscrewed channel and compare them. And if those two bits agree, then they'll discard those from the secret key, because anyone could intercept that and would have that information about it. If they don't agree, though, say Alice had a 0 and then Bob had a 1, in that case, they know that there was an eavesdropper, or at least some error along the line. And so how that kind of works out is that if Eve were to intercept these photons before they reach Bob in the first place, to calculate the actual bits, she would need to guess a basis for each one of those. And via the Heisenberg uncertainty principle, if she guesses wrong, then the information encoded on the other bases get lost. And so, since she's just guessing, she has a 1 out of 2 chance. So she'll average 50% of the time she'll be incorrect with her guesses. And it's the same for Bob, he has 50%. So if Eve guesses wrong 50% of the time, then that means that 25% of Bob's will differ. So essentially that leads to the probability that Eve goes undetected is 3 out of 4 to the power of n, where n is the number of bits in the shared key. And so that way, the longer the photon sequence that you send for the shared key, that probability will just go towards 0 to the point where it would be negligible. And so QKD is a fascinating protocol, and it seems real cool, but there are some issues and limitations with it. For one, it doesn't have authentication for the transmission source, so Alice doesn't really have a way of knowing that she's sending them to Bob. Bob doesn't really have a way of knowing that he's actually receiving from Alice and not some random malicious third party. Another thing is that it requires a lot of special equipment. It's physical layer security, and so you kind of need a dedicated fiber optic communication thing, and some of these networks aren't really set up for that. And it's also difficult to upgrade, patch, or integrate into existing systems. So while there might be a lot of fiber optic systems set up for communications, it's difficult to add in and integrate the quantum aspect of it. And then once you do have it set up, it's difficult to really, if you find some issue with it, it's hard to patch that out. And then along those lines, the increased infrastructure costs is a big concern with a lot of these. It kind of leads to some other security issues. Because it requires all this special equipment that does cost a lot, then the infrastructure cost soars, and then that means they have less cost or less money to put into other security. It's also just generally limited by hardware designs because it is on the physical layer. And so a lot of the vulnerabilities in this come from the actual implementation of it and the hardware that people use for it. Because if there's a vulnerability in hardware, then hackers and malicious parties can take advantage of that. And there have been several public attacks on QKD systems in the past, so they are definitely not fully secure like it might seem. Another big issue is the denial of service risk. Because it is sensitive to an eavesdropper, it's nice being able to know that there's an eavesdropper listening in, but the issue comes from if that eavesdropper is always listening in, then you can't really ever agree on a key. You can't ever have real communication unless you have other channels. And even then, if there's an eavesdropper listening on all of those channels, then that essentially just denies service to that person. And so for future work and research, like we said, QKD is not really ready for large-scale implementation. There's still a lot of issues, cost issues, and just hardware limitations that need to be fixed first and developed more. With the hardware design and all that needs to be improved upon. Another thing is just that since it relies on quantum computing has come a long ways, but it's still, in a lot of development. There's still a lot of research and work going into it to improve it, to make it kind of commercially viable. And along with that, QKD is not the only solution for, once the world switches to quantum computing or it becomes, prevalent. There are other cryptography standards that people have proposed and been developing that are able to resist quantum computing, and they're secure against that, but don't necessarily have some of the cost and infrastructure needs and possible security issues like QKD. So in conclusion, quantum computing poses a serious threat to existing cryptography standards because as it is, we rely on things being infeasible, but quantum computing is great at solving those problems. One such possible solution is QKD, quantum key distribution. And while it seems like a pretty great solution, and could be if it's developed more, currently just the hardware limitations, the cost of it, and the other associated security risks prevent it from being the standard protocol and cryptography standard in the future. And there are all my sources.